Welcome to EDU World Space.
So in this question, the statement states that initially the gaps between the A-36 steel plate, right? Now it means that the material that we have over here is steel, right? And the rigid constraints are shown in the figure. Now determine, we are required to determine the normal stresses, right? And that is sigma sub x and sigma sub y, right? In the plate, and it says that the temperature is increased by a factor of del T that is equal to 100 degree F, right? Now, the hint that is given to us in this question is that if we want to solve it, we need to add the thermal strain, right? Now, what is a thermal strain? Thermal strain, that is alpha times del T, to the equation for Hooke's law, right? So let's take a look at the solution. Now, the question is very simple. So now, the first thing we need to do is to see if the elongation caused by the increase in the temperature is bigger than the gaps between the plates and the wall, right? And why we need to see is that because if it is in bigger than the gaps between the plates and the wall, then there is no stress whatsoever, right? So it means that the strain applied from the temperature um, will be given by this expression, that is epsilon sub t equal to alpha del times del t, right? And that is equal to 6.6 into 10 raised to the power negative 6 into 100, and that is equal to 6.6 into 10 raised to the power negative 4, right? Now, from where did we get this alpha's value, right? We got it from um, the book, right? It is present at the end of the book, and its alpha has a value of 6.6 into 10 raised to 1 negative 6, right? And n sub v is equal to 0.32, right? And the elasticity for steel is 39 into 10 raised to power positive 3, right? So now that we have the strain applied by the temperature, right? We have its value. Now what we're going to do next is that we are going to recall that elongation follows the rule, right? So the elongation follows the rule that epsilon is equal to del L divided by L, right? So it means that del sub x t is equal to L sub x into the strain caused by the temperature, right? And we have the values for both of these variables, so I'm just going to plug them in. So when I plug them in, I'll have 8 into 6.6 into 10 raised to the power negative 4, right? And that is equal to 0.0052 inch, right? And this is greater than 0.0025 inches, right? Now, next, what we need to do is that we need to calculate del sub yt, right? So that is equal to L sub y into uh, the strain caused by the temperature, right? Again, we have the variable for both of these values for both of these variables, right? So just plug them in and we'll get our answer. So it's 6 into 6.6 into 10 raised to power negative 4, right? And when you calculate it, you will get that it is equal to 0.00396 inch. Now again, this is greater than 0.0012 inch, right? Now, since the walls won't allow the plate to elongate that much, right? So it will apply normal stresses to it, right? So it simply means that um, the since the I'm just writing down what I have just said, right? So it would be easier for you to understand that since the walls um, won't allow the plate to elongate that much, right? So it will only apply normal stresses to it, right? Now, as you can see that it is much greater than these values, right? The calculated values are much greater than these values, right? So that is the reason why it won't allow the plates to elongate that much, right? And will only apply normal stresses to it. Now, what we are going to do is that the elongation, the stresses um, will cause, they will be opposite in direction, right, with those of the temperature. So let's take a look at their values. Let's try to find them out, right? So we have del sub x w, right? That is equal to 0.0025 negative del sub xt, right? So again, we have their value, just plug them in and you'll get that it is equal to negative point zero 0278 inch, and then we need to find it for the y direction. So that is 0.0015 negative del yt, right? And that is equal to negative 0.00246 inches, right? Now what we are going to do is that we are going to use the elongation formula, that is strain is equal to del L divided by L, right? And then we'll use it, we'll get that the strain in the x direction is equal to x sub w divided by L sub x, right? Now again you have the values, these newfound values, right? I'm talking about these values. So these values as well as you had these values earlier, right? So I'm just going to plug them in over here. So we have negative 0.00278 divided by 8, and that is equal to negative 3.745 into 10 raised to power negative 4, right? And then we need to find out the strain in the y direction, so that would be x sub omega divided by L sub x, right? And that is equal to negative 0.00246 divided by 6, and that is equal to negative 4.1 into 10 raised to power negative 4. Right now, what you're going to do is that we are going to use these equations. Um, we are going to use all of these new found calculated values in the equation 10.30, right? So equation 10.30, sigma the strain in the x direction, right, it is equal to E divided by 1 negative the square of the epsilon, right? Then in the parentheses, we have the strain in the x direction plus epsilon times the strain in the y direction, right? Now again, you have the values, just plug them in and you will get that it is equal to negative 15.466, and that is approximately equal to negative 15.5 ksi, right? Then we need to find out the strain in the y direction, right? So that is equal to E divided by 1 negative the square of the epsilon, right? And over here we have the strain in the y direction plus epsilon times the strain in the x direction, right? Then just plug in the values, the given values as well as the calculated values, right, that we just found, and you will get that it is equal to negative 16.8391, right? And that is approximately equal to negative 16.8 ksi, right? So this concludes our solution for this